All right, back again. We've got took care of Mario's problem over here with dealing with Luigi's problem. Is this one easier? Yeah, probably should be easier by now. I sort of built in some practice over here so you can do it again. I gave it a little easier, maybe a little easier. The radius is 5 on this thing. I think that makes it a little easier. You don't have to think about the diameter and cutting it in half. It's still the same situation where this pipe is 6 inches thick. So if the radius is 5, and here I'm kind of showing it again, the solid pipe, subtract out the water to get the actual thickness of the pipe. So I'll have how much water, I'm going to get that as one answer, and then the subtraction of the 2 is my other answer. So the height's the same for both of these situations. It's the same thing I did it over here, just did it as two separate problems. Here I've got it kind of built into one. The height is 15, we know that. The radius is different. The radius of the thing solid would be 5. The radius, if you subtract the 6 inches, would be 4.5. I'm pretty sure you should get 375 pi and 303.75 pi. This would be the volume in terms of pi of water. This would be the volume as if it was solid. If you subtract those, you get 71.25 or 71.25 pi. And of course, if you did it as a decimal, you get 224. So it's kind of interesting. These answers are very close to each other. This one had a longer length, but a shorter diameter. This diameter would have been 10, and this had a shorter length. So, you compare the two. This is a little bit longer. This is a little bit larger radius. Kind of balanced out. So hopefully that made sense the second time through that. The first one is usually a pretty challenging problem. It's not a basic problem because of the fact that it's hollow and I'm asking you to subtract. So the second part of the notes, you should be able to do the entire homework just based on that, based on those couple examples on there. The second part of your homework, and this is really going to be your weekend homework, if you check Schoology, you can work ahead, talks about cones. I'm trying to avoid the cones for the most part on Thursday night's homework. So a cone, talk about the base again, you can tell what's true about the base. What kind of base does a cone have? And of course that's a circular base. So again, pi r squared will come up and 2 pi r come up again. And then of course this is the definition for a cone. It's got circular base and it's got some other point that is not in the same plane as the base. And of course from pyramids, that point is called a vertex. So over here I kind of labeled some stuff. The vocabulary for cones is pretty much the same as it was for pyramids. You can tell what I'm pointing to inside the cone. What's that dimension inside the cone called? And you go, okay, that's the altitude, or that's the height of the cone. What's this sort of slanted one called? Oh, that's the slant height. Now it's a little different for a cone because the slant height is sort of infinitely all the way around the edge of the cone. It doesn't really have an edge. And of course that's pointing to the vertex up top. So we talked about this with the pyramid. It's the same deal with a cone. The height of a cone is an altitude that goes to, think about where that hits right there. It hits the center of the base, the center of the circle. It hits right smack dab in the center. I won't fill these two in for you. You can do that. It's sort of logical that the altitude has to hit the center of the cone as long as it's a right cone. And I'm not going to do anything with the oblique cones, so you don't have to worry about that. Oblique cones would be ones that are sort of, this point is over here and it's sort of stretched sideways. And of course, there's slant height again. Slant height of a cone is a segment from the vertex to the blank of the blank. It goes from the vertex down here to the edge of this base, or to the outside of the circle. You can call it either one. And of course, you could draw that segment an infinite number of locations. Like you could draw it here, it could go on the other side, it could go anywhere to anywhere along that base. So I give you, and there's an example built in here. There's labeling my vocab on there. There's an example I think I built in on here about the ice cream cone. Gosh, this makes you hungry, doesn't it? So the height is 7, and you can use this or this drawing. Let's say the diameter was 10, the height is 7. Find the slant height. And just like you did with pyramids, that's supposed to be a cursive L again. I know it's a little small of a font here. Cursive L, find it. Find the slant height. And just like you did with pyramids, you got to use Pythagorean theorem. And you know it's not 10 squared. If the diameter is 10, radius would be 5. So you're doing 5 squared plus 7 squared, and you end up with who knows what. I mean, you can add that up on your own. Simplify it if you want to leave it as simple as radical you can. Get a decimal. It's obviously going to be more than 7. So this was the homework. I'm hoping the cylinder part of the homework is pretty easy for you. I'm going to jump over this for a minute. I intended on pausing on this no matter what and doing this a separate day, but I'll jump over it right now so you can kind of have an idea. Fill in an analogy here. Not a simple analogy, I don't know, with all the shapes you've covered so far. So we covered prisms, we covered pyramids, we covered cones, we covered cylinders. So a good spot to pause. Can you figure out how a cylinder and a prism and a cone and a pyramid relate to each other? And an analogy is those things on the SATs that are, designed that you only know like 2 of the words, and they give you 4 words in sort of a ratio format or proportion, kind of a proportion format. Oh, sorry about that. So one way you could do this, you could say a prism is to a cylinder. If I did prism to a cylinder, if I started with prism, I'd have to start here with pyramid. A pyramid to a cone. You could do a prism is to a pyramid. And if I did prism pyramid, I'd have to do cylinder cone. There's a lot of different ways to sort of correspond these shapes, but they're directly related. So I'll come back to that apparently later. I'm going to dive in and talk about the cone shapes on here a little bit. Some of this we have to derive, and some of this is pretty easy and logical. What's the shape of the lateral surface of a pyramid? We talked about this the other day. And of course you remember they're all triangles. How do you find the area of a triangle? Well, you know that's 1/2 base times height. So that's stuff you're familiar with. And I have base times height. I also threw this base times slant height, because that's the whole reason we talked about slant height is important. Slightly different formula for cones, because these aren't triangles. If you think of what this would look like if you unrolled it, it's not quite a triangle. It says to sketch the lateral surface of a cone. In other words, if I told you to take out a piece of paper and scissors and make a cone, you'd have to cut something that looks kind of like this. It's got a circular edge here, and of course I'm hoping you realize this edge is the circumference of the final cone. This slanted length here, that's here and here, which is interesting, this is the slant height when you're finished, because you'd bring this edge all the way over to this edge. So there's the slant height on either one of these. The slant height is kind of like these 2 dimensions on here, which if you look at that, it's sort of like a little curved triangle. So it's going to be very closely related to this. Treat this like a triangle. What's the base of the triangle? Well, the base of the triangle is the circumference of a circle. It's 2 pi r. It's the circumference of the final surface on there, the final cone, the final base of the cone, I should say. And what's the height of this? And I don't care if you draw the height here, and you want to draw it as an altitude usually, but in reality this is the same as this and this and this, because it's circular. It's sort of like these are all the same. So I don't care where you draw that sort of imaginary altitude in. That altitude, we said a minute ago, that's the slant height of the final thing. If you were to roll this thing up, that's your slant height. So if you really want to understand the formulas I'm going to throw at you here, you want to make sure you understand it comes from a triangle that's sort of circular on here. The base of the triangle, and you can see how it kind of looks like a triangle, is the circumference of the final cone. And the height of the triangle is the slant height. This is your formula for the lateral area of a cone. It hasn't been simplified clearly. I've got 1/2 times 2 times pi times r times L. What's kind of nice about how this simplifies? And hopefully you're going, oh, 1/2 of 2 is just 1. You can cancel those 2 out. This is the lateral area of a cone. Pi r L. It is that simple. Pi times r times the slant height. But just so you know where it comes from, again, it comes from this sort of imaginary sort of circular triangle. I'm going to pause this thing because if I don't, I'm going to run out of time on here. I'll be back momentarily.